That is always true. Unless this integration, this domain of integration does not include sound source. Right? Okay, in this domain, has to be satisfied, or I can say capital P that I call Helmholtz equation. Must be satisfied in this source-free region. Okay? All right. All right. This term and this term, what those terms really implies. I do understand every student are not very happy about handling this strange Kirchhoff-Helmholtz integral equation. Is there anybody who is very happy about it? Okay. This is the integral equation. So I suggest you to see the appendix. Okay. I tried the Kirchhoff-Helmholtz integral equation in 1D case, one-dimensional case, using separation of variable. That is fantastic. I mean, start with the one-dimensional case. You may be able to, not maybe, but I'm sure you can understand what does that integral equation really works for predicting the sound at a point that we do not know. Okay? So appendix C, one-dimensional case. And then go to 3D case. Most difficult case is a 2D case. So omit to understand 2D case. When 2D case is very difficult. For example, when you try to understand wave propagation in membrane, it's not easy, but it's much better to understand the sound radiation in 3D. The 3D sound, for when I whistle, the sound is radiating like this. But suppose what would happen in 2D case? When you hit the membrane, if membrane does not have a damping, okay, the radiation pattern would not be like a 1 over R as it observed in 3D, right? It turns out it is 1 over square root R, and that is not easy to understand. Okay, so 1D case and look at 3D case. Okay. Now our job is to apply this equation for this case. You see? Okay? Now you can do it. You can do it. First step, you have to select the Green's function. How to select the Green's function? First, you have to select Green's function. What is the necessary condition for the selection of Green's function. What Green's function has to satisfy? Huh? Boundary condition. Exclamation. Anybody who opposed to this statement? Okay, remember when we derived the Green's function, we said this Green's function has to satisfy this inhomogeneous wave equation, right? Physical meaning is that we are exciting the sound field at r equal r0 using unit delta function. In other words, impulse. Does this equation has boundary condition? No. Then does it mean that this statement is wrong or X? Okay, let us leave this for very good candidate for your scheduled quiz on Thursday. Okay, Yunjae and you might have some good discussion after this class. Okay, and then how to select S0 integration surface. That is another problem. Do you think this integration surface is the best in terms of convenience of really performing integration? Okay? So in the last lecture, I hope you guys remember this, on this surface, the boundary condition is fluid particle cannot penetrate the surface. In other words, rigid wall. If I write the rigid wall condition mathematically, then I can write dPdN has to be 0. Right? Because Euler equation says dPdN has to be 0. Okay? If I select Green's function as Yunjae suggests, to satisfy this, what is the advantage? Okay, not easy to answer directly. But in the last lecture, we selected surface of integration like this, right?